In the next section, we're going to talk about some irrational numbers and radicals. Now, this one is for sure a section that is combined between different sections in the textbook. But again, it's because it makes a lot of sense to treat them as being together. At the same time, dealing with the fact that both concepts that are done are both relatively simple to understand, aka they're just really short, so in order to have a lot more content within a lesson, instead of you all being done within 20 minutes, at least extend it out towards an entire hour. But the main reason being that they are really closely connected. So we'll talk about two definitions. We'll talk about one definition that we had done last year in grade 9, and then extend it on to our grade 10 definition. So our rational numbers are numbers that can be written in the form a over b, where a and b are relatively private integers and b cannot equal 0. In other words, a rational number is any number that can be written as a fraction. Now, the other forms of that is basically the decimal of a rational number either terminates or repeats. So for example, if we look at the number 9 over 5, well, that's 1.8. Or if we look at, really, we'll say 1.3 repeated. Well, that's still a rational number. That's 4/3. Any number that you can write as a decimal or as a fraction, well, as a fraction, are decimals that terminate or repeat. Now, you can have negative numbers included in that, like negative 2.71673, and that 2 being repeated, that's still a rational number. So that is your grade 9 stuff. But where we go further into grade 10, we talk about irrational numbers. So an irrational number is a number that cannot be written in the form a over b. Now, previously we had done a full chart where we talked about our natural numbers, we talked about our whole numbers, then we did our integers, and then we talked about our rational numbers. The symbol for rational numbers being a barred Q. And an irrational number is a barred Q with a line over top. So that dealt with our there. We had done a chart similar to this before, and then we extended on to complex numbers, but talking about these ones being our real numbers. So an irrational number is just something that can't be written as a fraction. Again, a and b are relatively prime, b can't be equal 0. Now, the overall idea behind the decimal of an irrational number is that it doesn't repeat and it does not terminate. So numbers like pi, 3.14159265358979323846264, blah, 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 blah. We keep on going. I'm still working on some more than that, but I'll keep on dealing with that. Another famous number is E, which is 2.718281828. Even though it repeats in that section, it does go farther. It goes 904,590, and it doesn't keep on repeating after that. It is still an irrational number. So any number that you can just keep on going without any kind of rhyme or reason, like negative 1.234652331, and as long as it doesn't repeat, you have an irrational number. Now you do have to be careful. Your calculator may look like it has a repeating or may terminate, but you have to be cautious. For example, the number 2/3. Well, that's going to be 0.66666. Yes, the 6 keeps on repeated, but on your calculator, the last digit comes out as 7. Well, that's just because your calculator ends. That's what you see in your screen, But really, the only reason that that 7 occurs is because the 6's keep on going. You look at this 6 is going to round that 6 up to a 7, and that's why you have that number. You have to be cautious of what you see in your calculator. You can't just say, oh, it ends. No. You have to use a little bit of reasoning with what you're doing. So before we keep on going on, we're going to talk about more irrational numbers. And some irrational numbers occur when we have square roots or cube roots, and even higher numbers. So in order for us to access our square root, which is the radical, which is the thing that we talked about in our previous section. No, previous section? No, one of our previous sections. In order to access your square root, most calculators access it through a secondary function, which means that you do have to press second first on the Texas Instrument X2S. You have to press second x squared, because what that will do is it will access that square root button. So for example, if you wanted to say find out the square root of 64, you would have to type in second, press your x squared, which will access the square root character, and then you just have to type in 6, 4, press equals, and you get 8. Some calculators, for example, the Texas Instruments XA, does access the cube root. So what that is, it is a 3 as your index with your radical. Most calculators, though, so on the XA, I believe it has an actual cube root character, usually accessed through a second function. On the X2S and on many others, what you have to do is you have to type in a few things. You have to type in the number 3. Then you would access your second calculation. On the X2S, it's on this one. On Sharp and Casio calculators, it can be almost anything else. I just don't have any calculators like that on me, but it will access this X root button. So we'll have a little X in here as your index. Typing in the 3 first means that it will actually automatically input that 3 into that X. So if by chance you were wanting to find out the cube root of 64, you would have to type in the number 3 first, then go second to access this X root. Oh, I'm sorry. That's on the X2S, it's the power, which accesses the X root. And then I'd have to type in 64 and comes out as 4. So what's the connection between, or what is square root and cube root? Well, square root means basically 8 times 8 equals 64. If I want to find out the cube root, well, that's asking 4 times 4 times 4 equals 64. If you want to find out any higher number, for example, if we wanted to find out the 4th root or the 5th root, the only thing that would change is you just have to change that 3 to a 4 or 5, or so on and so forth. So that's kind of the basic things first. We'll come back directly to this in just a second. But before we go any further, we're going to talk about what rational and irrational numbers are again, and we're going to do some ordering. So again, rational numbers are anything that can be written as fractions. Irrational numbers are things that can't be written as fractions. Examples of fractions are numbers that, if you have your decimal form, they either terminate or they repeat. Irrational numbers, the number does not repeat. So are the following numbers rational or irrational? Well, the basic way of doing it is either understanding what your rational number is, which means it's a fraction, or understanding what the decimals look like. So first off, we do have a fraction. So a fraction means it's rational. Symbol. Oh, sorry. Those are cute. At the same time, if we were to type in -2/5, it would be -0.4. If we want to find out our square root of 5, well, we're going to have to use our calculator. Square root of 5 is going to be 2.236067977. Well, none of these decimals look like they repeat. Same time, it's just going to continue on, which means that this would be an irrational number. If I want to find out the cube root of -12, well, I'm going to type in 3, my second function, access my xth root, type in -12. I get -2.2894284845. As of right now, it for sure doesn't look like it's going to be repeating. There's no, see, I see it 289, 284. 894, 848, 85, still doesn't work out greatest. So this one is going to be an irrational number. The cube root of 27. Well, we type it in, number comes out as 3, which means that is for sure a rational number. I want to find out the fourth root of 26. I'd have to type in 4, access my second, type in my xth root, 26. I get 2.258100864. Again, doesn't look like there's any repetition. It's going to keep on going on, making it an irrational number. So the task is we're going to order these numbers. Are the following numbers rational or irrational? Okay, we've determined whether they're rational or irrational. We're going to order them from least to greatest. One thing that I always encourage and always, sorry, not encourage, I expect is if you're ordering numbers, order the numbers you're given with, or that you are actually given. If I write 2.236067977, that is not the square root of 5. That's a decimal approximation because you can't write enough decimals to have exactly the square root of 5. Why am I going to write 2.236067977 when I can just write square root of 5? So if I want to go from least to greatest, my least number is this -2.289, but the number that it actually is a cube root of -12. The next number that we're working with, well, our next highest number is -0.4, which is -2/5. Obviously, if you're already given something that is a decimal, for example, if this number was actually -0.4, I'd put -0.4. That's not the case here. Next number, well, we're looking at 2.236 or 2.258. Well, obviously, our next largest number will be the square root of 5. Then the fourth root of 26. Oh, that's wrong. That is not the number that was given. Even though it does work out perfectly, it's not what I want. I want you to order these numbers from least to greatest. It's the cube root of 27. And there's our ordering. I have some very short questions on that one. Now we'll do some recall here. So for example, we'll look at the few different things. For example, the n being called the index, the x the radicand, and the entire thing being known as the radical. So I talked about it before, but we'll talk about it again right here. When we're looking for the square root of a number, you're looking for something that when multiplied by itself produces the original number. That's what we talked about right above here. If we're looking for the square root of 64, we're looking for what number multiplied by itself gives you 64. Well, it's 8 and 8. Of course, at the same time, that's also negative 8 and negative 8, this being known as the principal square root. Well, pretty much we're going to talk about a lot of principal square roots in grade 10. Grade 11, we're going to be talking about the principal and non-principal square roots, which means we talk about the negatives as well. But we'll kind of work with that next year. Cube roots, same principle, but only with the same number times itself 3 times. So the cube root of 64, well, that's 4 times 4 times 4 equals 64. You can't get positive 64 by 3 negative 4s. This is your only answer. Same time, if I look at this one, I could take negative 2.289428485. Its full actual decimal value, multiply it by itself 3 times, or put it to the power 3, and I will get negative 12. So our second example, we're going to talk about and connect what we're going to be dealing with to concepts that we did in grade 8. Now, later on, again, keep in mind, I keep things out of order, so meaning that we haven't actually done our surface area and volume unit. But we've dealt with this formula not last year, grade 8, and we'll be dealing with this kind of stuff a little bit later on. First question is, what is the cube root of 1,728? So, if I want to find out what is the cube root of 1,728, I have to just use my calculator. I used the wrong character. It's going to be 12. So part B says, if a cube has a volume of 1,728 inches cubed, what is the surface area of the cube? Well, let's do some visual here. Let's deal with actually having a cube. Please ignore the slanted lines that are not actually making it a cube. So we have a cube that has a volume of 1,728. Well, the beautiful thing about a cube is that every single side is the exact same. At the same time, we know the volume of a cube being the area of the base multiplied by the height. In this case, the base is a square, or just a more direct rectangle. The layman formula for volume of cube, or any kind of rectangular prism, is length times width times height. But if all of our sides are the exact same, really we're asking ourselves, what number, I'll just say the length, add a little curl to it, make it actually look like now, what number multiplied by itself 3 times gives us this volume? In other words, our volume cubed is 1,000, or our length cubed is 1,728. And just like when we work with our Pythagorean theorem, if we want to get rid of our cube, we'd have to cube root. Obviously, Pythagorean theorem is squaring and square root. But if we cube root it, the length is 12. In this case, 12 inches. So each and every single one of these sides is 12 inches. So that's not what the question's asking for. It's what's the surface area? In order to go from volume to surface area, we need to find out what is one side. Sorry, what is one edge? From there, we just take it a little bit further. To find out the area, well, each of our sides are squares. which technically is for a square, it's side squared. Same time, many people use length times width or base times height. All are perfectly fine. Really, it's just going to be 12 times 12 no matter what. Unit being inches squared. But that's only one side. On a cube, there's 6. So our surface area of this cube will be 864 inches squared. Again, I have a few quick questions on that one, just because it is still dealing with our cubes, and you've dealt with these formulas before. You dealt with them in grade 8. Surface area being also extended to grade 9, and if you've already taken the workplace, you got it there too. So we talked about primes, we talked about irrational numbers, we're talking about how to find out cubes and square roots using our calculator, ordering numbers. Well, what does that all mean? Well, we're going to talk about some more roots. We're going to talk about radicals. Before we talk about radicals, we're going to talk about the prime factorization of 45. Well, prime factorization of 45 is 3 times 3 times 5. I can break it down. It's 9 and 5. There's our prime factorization. So if we were to type in the square root of 45 into our calculator, we're going to get 6.708203932. If I type 3 multiplied by the square root of 5, I also get 6.708203932. Obviously, the decimals are also going to continue on. One thing before we keep on going, though, that 3 is not the index. It is not a little number in here. If the number is not stated in here, it is a 2. This is a big 3. This is actually 3 multiplied by the square root of 5. That is one big, careful distinction that you need to make. You look down here, you'll see that this 3 is very small. This 3 is very big. You need to know that difference. So what we're going to do is we're going to notice a few different things. If the square root of 45 is the exact same thing as 3 multiplied by the square root of 5, well, what does that have to do with the prime factorization of 45? It's exactly this. The square root of 45. Well, instead of writing 45, sorry, I'll add a little ledge to that one. Square root of 45 is the exact same thing as 3 times 3 times 5, all under the square root. But if I know that my index is 2, how does that lead us to say that it's the exact same thing as 3 times the square root of 5? Hopefully you can see that this 2, well, there's 2 3s here. What we're going to do is we're going to be writing these as mixed radicals. In order to write something as a mixed radical, in this case, because our index is 2, we're going to be looking for a group of 2 identical objects. In this case, it's a 3. This group of 2 3s, just like when we did our greatest common factor and lowest common multiple, that group we only took 1 of. So we're going to take that 3 and put it in front. And all we're going to do is write down what is remaining. In that case, the square root of 5. It may not make the most sense right now, But let's deal with some more questions. For example, the square root of 63. Well, 63, if I write down the prime factorization, 63, I break it down, would be a 3 and a 21. 21 breaks down to a 3 and 7. So I'd have a 3, and a 7. Because there's no number stated here, our index is 2. Which means what we're going to be doing is looking for a group of 2 identical objects. In this case, 2 3s again. So that group of 3s, we take that one group out, and we simply write down what is remaining. 54, same thing. 54 is a 9 and 6. Well, that breaks down into 9 breaks into a 3 and 3, 6 breaks down into a 3 and a 2. So what we're going to be doing is instead of taking the cube root of 54, we need to take the cube root of 2 times 3 times 3 times 3. Now sometimes that may not be more, it may not be more beneficial to write it like this. For example, you may feel like you want to write it in the condensed version. For example, 2 times 3 cubed. Both ways are perfectly fine. But we're still going to be doing the exact same procedure. Because our index here is a 3 now, we're going to be looking for a group of 3 identical objects. In this case, those 3s. I'm sorry for using a whole bunch of 3s. Well, I'll be getting away from the 3s in just a second. But because we're looking for that group, and we have a group, one group of 3s, we're going to take that one group of 3s out in front. What we have left is the cube root of 2. Now that 3 is extremely important to keep, because if you don't have that 3, it means that you have 3 times the square root of 2, which is not what this question is. It's 3 times the cube root of 2. We're taking the cube root of 54. We need to make sure we have a cube root in here. There is one exception, but we'll deal with that when we have it. 1600. 1,600. Should be a 40 and a 40, right? Yes. Now 40 can be broken down into an 8 and 5. Now I know that I usually don't write my factor trees horizontally. It's just because of my space. 8 is 3 2s. I know that I've shown this skill already. Sorry, just tying back to this first one. Because I'm looking for the group of 3 things, I can look for this right here. I can see that I have a group of 3 left. I have 3 3s. I can take that entire group right there. And we still get the exact same answer. Sorry, I digress. Cube root of 1,600. Again, 2 ways of doing it, but I have 3 6 2s and 2 5s. That would be the exact same thing as having 2 to the power of 6 multiplied by 5 squared. So where does this change if we have groups of 3? 3 identical objects. Well, we have one group of 3 identical objects, and we have a second group of 3 identical objects. This one, there's only 2 5s. We don't have a group of 3, so we can't actually take that in front. Because we have 2 separate groups, we'd have to take both groups out and put it in front. We have the cube root of what's left, 5 times 5. Please always simplify it if you can. 2 times 2 is 4. Cube root of 25. If we're doing it on this side though, if we're looking for a group of 3, well, 2 to the power of 6 means that we have How many times does 3 go into 6? Well, it goes in 2 times. So we'd have a 2 come out 2 separate times. Still be taking the cube root. Now, because 3 does not go into 2 evenly, we'd still have that 5 squared left. We still get 4 cube root 25. Or in other words, 4 multiplied by the cube root of 25. Same kind of stuff. 400 will be a 20 and a 20, which is a 4 and a 5, or each of those 4s being 2 2s. So we want to find out the cube root of 400. What we're actually doing is we're finding out the cube root of 2 times 2 times 2 times 2 times 5 times 5. Now, because we're looking for a group of 3, so I'm just making this a little bit higher here. I just want to show the exact same way if you do it like this. We're looking for a group of 3 identical objects. In this case, we have those 3, which means that we only have one group of 2s that can come out. We have a singular 2 left and 2 5s. That is not a group of 3. Even if you were to take a mirror and treat the 2 as a 5 or both 5s as 2s, that's still not the exact same thing. 2 is not the same as 5. So if I take my group of 2s out, I only have one group of 2s out. I then have the cube root of whatever's left, 2 times 5 times 5, being 50. Alternately, if you do it this way, how many times does 3 go into 4? Well, it goes in 1 full time. How much would be remaining? 1 would be remaining. So how many times we can actually take that 2 out depends on how many times the 3 goes into the 4. In this case, it comes out 1 time. And we still have 1 2 left over. The answer still stays as the exact same. How about 4th root of 128? Well, if we've done square roots and we've done cube roots, 4th roots should be no different. Say 128. Yes, it's even. At the same time, I know that the last 2 digits are divisible by 4. So I can use 4. 128 divided by 4. Oh, calculator needs to be on. Is 32. Now 4 is a 2 and a 2, and a 32 is actually 5 2s. So either we can write 4th root of 2 times 2 times 2, 2, 2, 2, 2, or we can write the 4th root of 2 to the power 7. In this case, because it's 4th root, we're looking for groups of 4 identical objects. 1, 2, 3, 4. 1, 2, 3. Nope, that's not a group of 4. So I can take my one group of 2s out. 4th root of what's remaining? 2 times 2 times 2 is 8. Or how many times does 4 go into 7? Well, it goes in 1 time. How much would be left over? 3 of them, which leaves us at 2 4th root of 8. Exact same answers. And finally, 300. Let's see, I can do 10 and 30. A 10 is a 2 and 5. A 30 is a 6 and 5. 6 is 2 and 3. Well, it means I'm dealing with square root 2, 2, 3, 5, and 5. Because it's square root, the index is implied to be a 2. So we're looking for a group of 2 identical objects. Notice how every single time I've said identical objects, I have not said group of 2. 2 identical objects. That's 2 identical objects. That's 2 identical objects. I take my 2 and my 5 out. I'm left with the square root of 3 underneath. I do have to multiply that 2 and 5 to give me 10. So these are examples of writing things as mixed radicals or writing them as simplest radicals or in simplest form. There is another thing that we have to do. We have to talk about writing things as entire radicals. Well, that actually just means going backwards. Just going from 3 cube root of 2 to cube root of 54. Well, how do we do that? Well, we use the exact same terminal, or just basically opposite terminology. If in this one I'm taking a group of 3's out, and I have that 3 out, well, I'm just going to do the exact opposite and put 3 3's back underneath the radical. So what that means is if I have that cube root, I have a 2 still left underneath, I'm going to take my 8 and put it underneath my radical 3 times. I get the cube root of 1024. If my index is implied to be a 2, I'm going to take the square root of 3 times 7 and 7. And I get the square root of 147. If I'm going to take this, a 5th root of 6 times, and I'm going to have 5 2's go underneath, I'm going to write it and make it still make sense. I'm going to take 6 and multiply by 2 to the power of 5. 5th root of 192. And there we go. Have fun.